Good morning, one and all. My name is P. Prasanth Kumar, pursuing M.Tech Power Electronics in Gokaraju Rangaraju Institute of Engineering and Technology, and I am here to explain about my project titled Design and Analysis of Non-Isolated Boost Converter and its applications are these are used in battery powered systems like hybrid electric vehicles and notebooks, laptops, and camera flashes.
My project title is Design and Analysis of Non-Isolated Boost Converter, and my guide is Mr. P.M. Sharma, Head of the Triple E Department. Non-Isolated Boost Converter is designed using the topology Non-Isolated Boost Converter followed by the 3-pin regulator. The controller used here is the TL494C, and the switching frequency of the switching element. Here the switching element used is MOSFET, and it is about 100 kHz. The simulation software used here is the MATLAB, and the analysis done here is mathematical model, the transfer function, and the frequency response is obtained. Non-isolated boost converter is simulated in a MATLAB software and waveforms are taken. Non-isolated boost converter is used in both AC to DC and DC to DC conversion. The output voltage is greater than the input voltage of the boost converter. It requires a single controllable switch like MOSFET, and usually the switching frequency is in the range of 100 kHz. Coming to the schematic of the boost converter usually employs an inductor, and there is no DC voltage isolation between the input and output. The figure shows the two configurations of a boost converter depending on the state of the switch S. The basic principle of a boost converter consists of two different states. In the on state, when the switch is closed, it results an increase in the inductor current. In the off state, when the switch is open, the only path offered to the inductor current is through diode D, the capacitor C, and the load R. This results in transferring the energy accumulated during the on state into the capacitor. The input current of the boost converter is same as the inductor current. This figure shows the typical waveforms of currents and voltages in a converter operating in this mode. The inductor current will be increasing when the switch is on, and it will be decreasing when the switch is off. The block diagram of the boost converter consists of a voltage source, magnetic field storage element, switch control, switching element, and output rectifier and filter. The voltage source provides an input DC voltage to the switch control and to the magnetic field storage element. And the switch control directs the action of the switching element, while the output rectifier and filter delivers an acceptable DC voltage to the output. Coming to the practical circuit of a non-isolated boost converter, the circuit consists of 5 different parts, and they are: first one is a power circuit, second one is a startup circuit, third one is a feedback circuit, fourth one is a maximum pulse width circuit, and fifth one is a IC controller circuit. Power circuit. The input voltage range given to the power circuit is between 8 volts to 12 volts. The circuit consists of a fuse of rating 2 amperes and an inductor, MOSFET, a diode, and an output capacitor. This is the startup circuit of a boost converter. The circuit provides the dead time control to the 4th pin of the IC controller TL494C. The dead time control maintains the minimum off time of the circuit. The input voltage given to the circuit is about 10 volts. The diode used here to avoid the reverse voltage. The input voltage will be maintained across the capacitor, and this voltage is given back to the potential divider, which provides the dead time control. The minimum on time is decided by the dead time control circuit. Now coming to the feedback circuit. The feedback circuit mainly contains the voltage divider circuit and also the compensator that provides the control and constant output voltage, although the input is varied. The output provided by the power circuit at the output capacitor is given as the input to the feedback circuit. The output of the feedback circuit is divided in the ratio of R4:R3 and given to the inverting pin of the IC TL494C. The output of the compensator is connected to the compensator pin of the IC TL494C, that is pin number 3. The feedback circuit filters the harmonics and gives the controlled output voltage. This is a maximum pulse width circuit. It consists of 2 transistors Q1 and Q2. The main purpose of this circuit is to limit the voltage. The base of the transistor Q1 is connected to the compensating pin of the IC controller, and the collector pin of the transistor Q2 is connected to the inverting pin of the op-amp, which is internally a part of the IC TL494C. The circuit consists of four diodes where the cathode of one is connected to another. The voltage drop across each diode is about 0.5 volts, and the voltage drop across the four diodes is 2 volts. The voltage drop across the transistor Q1 is 0.7 volts. The voltage drop across the diodes and transistors finally is about 2.7 volts. The excess amount of voltage coming from the controller circuit is limited up to the 2.7 volts. Coming to the controller circuit of the non-isolated boost converter, the controller circuit consists an IC TL494C. The switching frequency of the switching element is decided by the RT and CT. Here, the RT is taken as R8 and CT is taken as C2. By connecting this R8 and C2, a ramp voltage signal is produced and its magnitude is decided by the dead time control, that is pin number 4. The IC consists of two error amplifiers, of which we are using only the one that is connected to pin number 1 and pin number 2. The other error amplifier which is connected to pin number 15 and pin number 16 are grounded. The reference voltage which is connected to pin number 14 is divided by the potential divider by resistors R10 and R11 to a voltage of 2.5 volts and is fed back to the non-inverting terminal of the error amplifier, that is pin number 1, and the feedback voltage is connected to the inverting terminal, that is pin number 2. Here there are two inbuilt transistors in which the both emitters are grounded, and the collector C1 is connected with pull up resistor and collector C2 with a pull down resistor. There is an inbuilt PWM comparator which is connected to the base 2, and the pulses are taken out by pin number 11, and the output pin, that is pin number 13, is grounded. When error amplifier voltage exceeds the 2.7 volts, the pin number 3, that is compensation pin, gets enabled and the maximum pulse width circuit operates. State space analysis gives the transfer function for a system, and also it is helpful for getting the frequency response of a system. Here, the frequency response decides whether the system is stable or unstable. In my project, the state space analysis is being implemented to analyze the open loop transfer function of a boost converter, and it is helpful to get the frequency response of the open loop boost converter. The state space analysis is implemented for a boost converter, and the corresponding transfer functions are obtained. Compensator design is done both theoretically and practically, and their corresponding Bode plots are obtained. By comparing the theoretical and practical Bode plots, the obtained graphs are approximately same. Now I am going to explain about my project simulation, and it is done in MATLAB software. MATLAB is a high-level technical computing language and interactive environment for algorithm development, data visualization, data analysis, and numeric computation. Using the MATLAB product, we can solve technical computing problems faster than the traditional programming languages such as C, C++, and Fortran. This is a total simulation circuit of the non-isolated boost converter. The input voltage is taken as 10 volts, and the inductor is taken as value of 400 microhenry and a capacitor of 210 microfarad. The output voltage is divided by the potential divider and is compared with the reference voltage, and this voltage is given to the compensator transfer function, and this compensator transfer function is obtained by doing the state space analysis and frequency response, and this compensator transfer function is given to the PWM generator where the pulses are obtained, and these pulses are given to the gate of the MOSFET. And three scopes are used here, one for the output voltage and output current, and second one for the error voltage and gate pulses, and third one for the inductor current. Now I am going to simulate the circuit. This is the output voltage and output current waveform, and the output voltage is about the range 16 volts and the output current is about 0.56 amperes. This is the error voltage and gate pulses waveform. The error voltage is approximately 0 and the gate pulses are taken as 0 to 1. This is the inductor current waveform and it is ranging from 0 to 2.2 amperes. This is a simulation circuit using the step input. Here the step input is used to check whether for a change in input voltage there will be no change in output voltage and output current. For proving this, I am using a step input, and the total other circuit is same as for the above circuit simulation, and I am using a step input timing as 0.07 seconds. This is the output voltage and output current waveform before the 0.07 seconds, and this is the circuit after the time reaching the step at 0.07 seconds, and the output voltage is same as the above simulation circuit, and it is about 16 volts, and the output current is also the same, the 0.56 amperes. This is the error voltage and gate pulses waveform, and it is obtained, and this is the inductor current and it is ranging from 0 to 1.8 amperes. Conclusion: the 7.5 watts non-isolated boost converter is an efficient step-up DC to DC converter and is used in numerous electronic devices. The circuit is modeled and simulated using the MATLAB software. A closed-loop model is developed and used successfully for the simulation. The converter has advantages like it has reduced hardware, high performance, less weight, and accuracy. The simulation results are in line with the predictions. Thank you for listening my section and giving me this opportunity.